Good morning, everybody. Going to give people about a minute to join, and then we'll start for today. Okay, while people are joining, let me just start with a little recap of what we covered on Tuesday. So big things I covered on Tuesday: center of mass and rotational kinetic energy. So up until now, pretty much we've always been considered objects to just be point particles. But if I consider a real object like a bat or a baton or a ball or a pen, and I throw it, what I would see is, if I treated the object as if all the mass was at a single point, the average position called the center of mass, what I would see is that object would follow a nice parabolic path, just as if I had thrown a ball. But in addition to that, what I'm going to see is the object will also be rotating about this special point called the center of mass. And that's just the average position of all the mass of an object. So I throw, let me turn this on. So if this was just me throwing a ball up in the air, it would follow this sort of path just like the bat did. But if I toss the bat up in the air, the center of mass of the bat would follow the exact same path as if I had just thrown a ball. But in addition, the bat is going to be rotating about this special point called the center of mass. And the equations for center of mass, let me get these lecture notes. It's basically a weighted average. And so the position of the center of mass, all I'm doing is, if I have a collection of particles, 10 particles, 5 particles, I'm just taking the mass of each particle times its distance from the origin, adding those all up, and then dividing by the total mass. So if I had, 3 objects, it'd be m1x1 plus m2x2 plus m3x3 divided by the total mass. Same thing for the y position. Now, that's if I had a collection of point particles. I did an example problem where here's just 3 point particles, and we wanted to figure out the location of the center of mass. Now, it doesn't matter where you define the origin. For this particular problem, I define the origin right here. Given that we found the position of the center of mass, the x position was 1.7, the y position was 3.3, somewhere here. Now, if instead I had chosen my origin to be here, and I do all the exact same calculations, I'm still going to find the location of the center of mass to be in the same physical spot. It's just going to have different x and y coordinates. Now, that's if I have a collection of point particles. In reality, if I have an extended object, this is going to turn into an integral. And you end up integrating x dm. And again, we're not going to do any of these integrals, but I just mentioned because the math is kind of cool. How do you do an integral with respect to mass? Well, if the object is uniform density, meaning the density is not changing, then I can write my dm as rho dv. And then I end up integrating with respect to volume. And that integral is going to depend upon whether you do cylindrical coordinates, spherical coordinates, rectangular coordinates, and so on. Other thing I looked at is a rotating object has kinetic energy even if it's not moving through space. So we've so far been looking like objects, let's say sliding across an inclined plane. Kinetic energy was 1/2 mv squared. Well, if I have an object that's not moving but just rotating, that rotating object, even though it's not moving through space, has what's called rotational kinetic energy. The way we would calculate it is, I would take an extended object like this, and I would just break it up into billions and billions and millions of little points. each one of these is moving, and they all have kinetic energy 1/2 mv squared. So if I were to add up the kinetic energy of all these little pieces, that would give me the rotational kinetic energy. Well, they all have different linear speeds, but the omega, the angular speed for all of them, is the same. One of the things we went through is tangential speed equals r omega. All objects in a rigid rotating body are going to have the same angular speed, but they're going to have different linear speeds if they're different distances away. So for all of these v squareds, I can replace it with r times omega. So the speed of this one would be r1 times omega. The speed of 2 would be r2 times omega, and so on. If I then put that in, what I can end up doing is factoring out all of these omegas because they're all the same. So what I get is 1/2 times m1 r1 squared plus m2 r2 squared, and so on. The end result is this kinetic energy of rotation ends up being equal to 1/2 times this sum over mr squared times omega squared. This sum of mr squared we define as something called the moment of inertia. It describes how the mass is distributed, and the farther the mass is from the axis of rotation, the harder it's going to be to rotate the object. So I, moment of inertia, it has units of kilogram meter squared. There's no special name for it. And it just describes kind of like mass. The more mass, the harder it is to accelerate an object. The more moment of inertia or rotational inertia, the harder it is to cause an angular acceleration. It basically resists rotations. And moment of inertia is always given with respect to an axis. So if I had a thin rod here, I would have different moments of inertia around different axes. So if I rotated this rod around this axis, I'd have a different moment of inertia as if I rotated it around the center. The more mass you have farther from the axis of rotation, the bigger the moment of inertia. Now, this equation, the sum of mr squared, would be if I had a collection of particles. For a real continuous object, again, this sum of mr squared is going to turn into an integral of r squared dm. And again, you would turn that integral dm into a volume integral. End result is, I'm not doing any of these calculations, they're not even done in the book, but there's certain objects that you do all the time that you want to know the moments of inertia. The ones that I kind of went through, thin rod about the end, 1/3 ml squared. Pulleys, anytime we have a pulley, and on Tuesday or Monday of next week, we'll start looking at torque. And for torque, we're going to start looking at the moment of inertia. For a solid sphere, like a solid ball rolling, it's 2/5 mr squared. And then for a cylindrical shell, where basically all the mass is on the outside, 2/3 mr squared. So the last thing then is, right now, kinetic energy of rotation is equal to 1/2 times I, which is the moment of inertia, times omega, which is the angular speed in radians per second. And that's kind of where I got to. Let me pause this, see if there's any questions I can answer just on anything I've covered so far. Okay, before we go into rolling motion, I want to actually share with you a really cool video. And yeah, let you see it and then see what your thoughts are. So let me bring this up. Okay, so I'm going to play this video. I'm going to give you a chance to vote and see what you think.
All right, here is the setup. I have a rifle mounted vertically, and we're going to shoot a bullet into this block, right into the middle of it. And so obviously the block is going to go flying into the air. But we're going to do this again, and instead of firing the bullet right into the middle of the block, we're going to shoot it off to one side. And I want you to make a prediction. Will that spinning block, when we hit it to one side, will it go the same height as this first block? Will it go not as high, or will it go higher?
Okay, so versus being shot in the middle when you shoot on the side is the question, right? Like,
yeah. How high will it go in comparison?
It depends on if the bullet stays in the block. And I'm assuming it does.
It does stay in the block,
It
yeah.
does stay
I
in the block,
guarantee you
okay.
that.
Same height. I'm purely basing it on just like an instinct that I have.
I feel like I'm being tricked.
I just feel like you're trying to trick us and that it's going to do something that we can't predict.
I thought the obvious answer is not as high, so I'm going to say higher.
I'll say higher, but it's going to like fly in a different direction. or something.
So you have angular momentum, which
Yeah.
is L,
Yeah.
and you have translational momentum, which is P.
Yeah.
When you hit it in the middle of the block doesn't really spin at all, so it just goes up a certain height. But when you hit it on the side of the block, it's going to be spinning, so it's going to have imparted some kinetic energy, so there won't be as much potential energy.
And so the total energy of the system,
Basically has to stay constant. And the kinetic plus potential, which would be the height it goes to, will have to be constant. So if it's spinning and has kinetic energy, it can't go as high. That's my prediction.
so my prediction is it'll go up, not as high, but it'll spin more if it's hit to the side. Am I wrong?
I want you to think, which do you think is the most reasonable, and then click one of the annotations above. All right, are you ready? Make your prediction in 3, 2, 1.
Ah! What happened to my screen? Okay, so I'm going to give you a second to actually think about this, and let me tell you that John and I and most people I talk to were completely wrong about the result. So you shoot something straight up, bullet right through the middle, you're going to have the block rise to a certain height. But if I shoot the bullet off to the side, that's going to cause the block to be spinning, which means it also has a rotational kinetic energy that it didn't have if it was just rising up. Given all that, take a second and let's actually, I'm not going to do this as a poll. What do you think? Is it going to go to the same height, lower, or higher? And you know, even though you could watch this video offline, let's just watch it. It's kind of a fun little Thursday thing, and I think there's a lot of really great physics in it. And so let's just take a look at the explanation. Bullet block explained.
In my last video, we performed an experiment in which 2 identical wood blocks were shot with the same rifle. One through the center of mass and the other one slightly off to one side. Now, if you haven't seen that video yet, then click here now and go and watch it. Or if you're on a mobile device, click the link in the description. So the question was, compared to the block shot straight through its center, how high would the block shot to one side go? Now, 60% of you predicted that it wouldn't go as high.
That's what I predicted. That's what John predicted.
Didn't seem as high.
Now, check out the high-speed footage.
Oh no.
You can clearly see that both blocks
What?
are the exact same height.
Oh, come on.
19% said that it would go higher, and only 21% correctly predicted that both blocks would go to the exact same height. So most of us got it wrong the first time around, and that includes Henry and me and Destin, who has a lot of experience with this stuff.
I mean, I can't tell you how many times I've hit wood with the rifle.
So even experienced and intelligent people.
So real quick, before I kind of give you the rest of the video, the spinning block obviously had more rotational kinetic energy than the block that wasn't spinning. So at the very highest point, one block is spinning, not spinning, the other block is spinning. So how did the block that was spinning, it obviously has more energy. How is that possible? It is cheating if you've seen it already. I've seen it like 10 times, so. Something to think about. So before I show you the rest, the spinning block at the highest point obviously has more energy than the block that's not spinning. They're at the same elevation, so they have the same gravitational potential energy, but one of them has rotational kinetic energy, the other one doesn't. Well, the energy it had must have come from the bullet. So how is it that the bullet has a different amount of energy in one case than the other? Let's watch the explanation, because there's some really cool physics in this.
We'll get it wrong sometimes. In this case, I think the result was particularly counterintuitive because the spinning block clearly ended up with more energy than the other block. So I asked you guys to make me a video response and explain what is happening. And this is what I received.
If you imagine the bullet traveling through the center of the block, then after the bullet
pause. I just had a thought, you know, just in terms of this lab number 10, this might be another cool little thing if you could possibly arrange to do something like this at home. This would be a great sort of at-home lab to do.
Whoa, that is a lot of video responses, and that's not even all of them. I've got to say, I was blown away by all of the great video responses I received. You guys are awesome, and I really, really appreciate all the effort you went to. You know, some of you actually replicated the experiment, perhaps with different setups. The experiment was featured on blog posts, including Scientific American and Wired. There's an interactive simulation you can try. A link is in the description. And someone even made a webcomic. It is so incredible. You know, watching all of those video responses, and I did watch all of them, that was my proudest moment making this YouTube channel. Seeing all of you guys doing science and getting so involved and putting in so much effort, it just blows my mind. It's amazing. Thank you guys so much. Thank you. Thank you. I can't even put it into words how awesome it is. Woo! So what is the answer? How could two identical blocks shot with the same rifle end up with different amounts of energy? Well, some of you felt that the amount of rotational energy would be basically insignificant.
What if the amount of energy necessary to get that very small block rotating really is negligible in comparison to the amount of energy necessary to lift it into the air and resist gravity?
Well, we can calculate it because the spinning block was rotating at about 11 times per second. So you can calculate that its rotational energy would be equal to 50% of the gravitational potential energy when those blocks were at their peak. So the spinning block actually had 1.5 times the energy of the non-rotating block. And in my books, that is not negligible. So what else could be causing this? Well, some of you actually measured the height difference using pixel counters and found that the blocks didn't go to exactly the same height. So this raises an important question, which is how different would those heights have to be before you can think that there really is a difference there? Well, given that the rotational energy is about 50% of the gravitational potential energy, you might expect the spinning block to go half as high. But looking at the video footage, you can clearly see it doesn't go half as high. It goes basically to the same height. To know for sure, you'd probably want to do the experiment a number of times. In science, you got to repeat things and make sure what you saw is not just a fluke, that it will happen every time. So in fact, we did repeat the experiment a number of times, and here are all of the blocks lined up side by side so you can compare their heights. The blocks clearly do not all go to the same height. So you might say, Derek, you were tricking us. You just picked the two that went the closest and used those. It's true, I did do that. But the point is, do the spinning blocks go systematically to a lower height than the non-spinning blocks? And I think from the video footage, the answer is clearly no. So why not? Well, another common response I saw was that air resistance must play a role, that the spinning block exposes a smaller surface area as it's traveling upwards, and this means there's less air resistance impeding it, so even with a lower velocity, it could make it to the same height as the non-spinning block. But you can do the calculation and find that the difference in air resistance would be at most about 0.6% of the weight of the block. In other words, negligible. So what is the real answer? Well, there are a number of ways of approaching the problem, and I saw you guys try almost all of them: force, torque, momentum, energy. But the easiest one of these is the law of conservation of momentum. You see, when the bullet is fired out of the rifle, it has a certain amount of momentum entirely in the vertical direction. And when the bullet becomes lodged in the block, the bullet and block together must have that same momentum that the bullet had. Now, it doesn't matter where on the block the bullet hits, because the bullet had a certain momentum before it hit the block and bullet together afterwards must have that amount of momentum upwards. So this means, regardless of whether the block is spinning or not, it must have the same upwards velocity so that it has the same momentum. So it will go to the same height regardless of whether it's spinning or not. It is simple conservation of momentum. Momentum is always, always conserved. It is something you can always rely on, and it's why you should think about it first. But some of you may say, okay, well, there's also angular momentum in the spinning block. But the point is, angular momentum and linear momentum are independent, and they're conserved independently. So you can simply think about the upward momentum of the bullet, and that's going to have to be the upward momentum of those two blocks. And it doesn't matter that one's spinning, because they have the same total linear momentum upwards. So they have to go to the same height. But if that is the case, why does the spinning block end up with this extra rotational energy? Well, the thing about energy is it's a little bit tricky. Although total energy is conserved, the energy of motion, which is called kinetic energy, is not conserved. So what happens is, as the bullet strikes the wood, a lot of its kinetic energy is lost, heating up the wood, creating sound, and deforming that wood block. So it would be possible for the rotating block to end up with more energy of motion, more kinetic energy, if the bullet loses less energy, deforming the wood and heating it up and creating that sound. And this kind of makes a little bit of intuitive sense, because if you imagine the bullet entering the block on the side, the block will be moving away from it faster because it's rotating. So that may mean that the bullet doesn't penetrate in as far, and so it wouldn't lose as much energy as it's entering the wood, which explains why the block has extra energy, allowing it to rotate and go the same height as the other block. Let's have a look at how far in the bullet went into each block. This is our first test. Here we go. This is the one where it went straight in.
There.
Yeah.
And we come over here to the off.
Let me pause that for
This
one
is where
second.
the bullet went off center.
Okay, so I will let people sort of watch the rest of that, but that is the end result. And I just wanted to mention it because we're starting getting further into conservation of energy. We're about to look at rotational kinetic energy and rolling objects. Momentum is always conserved in any kind of collision. So if I define my system as the block and the bullet, any forces they exert on each other are internal forces which are not affecting the total momentum of the system. But if you try and use energy, trying to use conservation of energy when there is a collision is extremely challenging, because heat is being generated, sound is being generated, some of the energy goes into deforming the block. So how is it that the spinning block had more energy than the block that wasn't? Simply because the bullet lost less energy in heating up the block, in creating sound when it hit it on the side. So there was more energy left over to cause the rotational kinetic energy of the block. Very, very cool sort of video and very counterintuitive. My initial thought was the spinning block at the highest point has to have more energy, so it can't go as high. And that's wrong, because we're trying to think of conservation of kinetic plus potential, but total energy is conserved, but not kinetic plus potential in this case, because some heat is generated, some sound is generated, the wood is getting deformed. Let me just pause for a second, open it up to any questions or comments about that video. You can sort of watch the end of it, very interesting, but momentum is always conserved in any collision. That's the first thing you should be thinking about. Conservation of energy can be tricky during a collision because it's hard to know how much energy is lost to heat, how much is lost to sound, how much is lost to deforming whatever the object is. Booyah! Questions I can answer on that. If not, we're going to move on to rolling motion. Firearms. That's true. So yeah, if you are going to try and recreate this experiment for Lab 10, do it in a safe manner and don't get arrested or anything like that. Okay, I think I'm only going to cover just rolling kinetic energy today, and then on Monday we'll do torque, and then I might stop for chapter 12. We'll see. I'm not going to be able to cover obviously as much as I would have covered had we been meeting live. Okay. Let's click your questions. PowerPoint. All right, so one, I mentioned that I can consider a rolling object to be a combination of two motions superimposed on each other. So an object which is just moving through space has translational kinetic energy. An object which is just rotating and not moving through space has rotational kinetic energy. Well, a rolling object is really just these two motions superimposed on each other. So an object which is rolling sorry, I just wait for a second. Forgot how long this was. Okay, so the point is I can consider a rolling object to be a combination of two kinds of motion. Just a motion without any rotation through space, just a rotation without any kind of motion, and rolling is just combining those two, which means a rolling object has translational kinetic energy 1/2 mv squared because its center of mass is moving. But it also has a, oh, why is this not turning on? One, come on. This thing does not want to work. Okay, so it has what we call translational kinetic energy, which is just the 1/2 mv squared that we've been looking at. But if it's rolling, it has a rotational kinetic energy also. And so now we're going to start dealing with rolling objects, and we're adding another energy term to all those different energies we've had so far. So you've got gravitational potential energy, you've got elastic potential energy, you've got thermal energy, you have translational kinetic energy 1/2 mv squared, but if it's rolling, now there's also going to be a rotational kinetic energy. And before I go into that, let me just say one thing about rolling motion that's going to be important. And I have no way of easily demonstrating this, but so I've got a wheel here, and the center of mass is moving forward some distance s. Well, what I could show you is that, well, I can't here, but as this thing rolls, it's going to move through an angle of theta. And if it rolls without slipping, how far it rolls linearly, s, is going to be equal to r theta, where r is the radius of the wheel, theta is the angle through which the wheel rotates. Well, what you can then show is that if I were to differentiate this, ds dt equals derivative with respect to time of r theta, what I would get is ds dt is really just how fast this wheel is moving through space. So it's my translational speed. And since r doesn't change, we're going to get this r d theta dt, which is really just r omega. So the speed at which the center of this wheel is moving is related to the speed at which it's rolling in terms of radians per second. And so I know that the wheel, so the speed of the center of mass of the wheel is going to be related to the speed at which the wheel is rolling. And talking about the fact that I can combine both motions, so I can treat rolling motion as two things. Everything in the wheel moving at some distance or moving some speed, the wheel just rotating, combining those two is what rolling motion is. So this right here would just be the wheel roll. This is the wheel moving without rolling, moving without spinning. This would be the wheel spinning, but not moving. And then rolling motion is really just a combination of those two. So if I think about it, looking over here, all parts of the wheel are moving to the right at some speed given by the speed of the center of mass, which would be r omega. If it's spinning, then remember our tangential velocity is always tangent to the path. So that the top of the wheel is moving to the right, the bottom of the wheel is moving to the left, right over here it's moving down. So rolling motion would just be combining these two, which means if I've got the top moving forward to the right at some speed, and because it's rolling, the top is moving to the right at some speed, what you'd see is the top of the wheel is actually moving at twice the speed that the center of the wheel is. And the bottom of the wheel, where it's actually touching the ground, is momentarily at rest. So kind of interesting, as this wheel is rolling, the top of the wheel is moving much faster, and the bottom of the wheel is actually instantaneously at rest. So have you ever seen sort of a picture of a spinning wheel? So here's a wheel which is rolling. You can clearly see that right here, you can see the spokes clearly. over here, the spokes are blurry. And that's because as this whole wheel is moving forward at some speed at the center of mass, at this top, the top is moving at 2 times that speed. And here the bottom is at rest. Just kind of a cool point in terms of rolling motion. Okay, what are we doing? 11:45. So the last thing then for this part is looking at kinetic energy of rolling. So as I was just saying, I can consider rolling motion to be 2 different kinds of motion. I can look at just the center of mass moving and just the object rotating about the center of mass. A rolling object has both forms of kinetic energy. And so now, whenever we're dealing with energy of a rolling object, you're going to look at 2 different forms. There's a 1/2 mv squared just because the center of mass of the object is moving. There's a 1/2 I omega squared because it's rotating. And so our kinetic energy of rolling, any rolling object I'm going to have is, what's going on here? It's going to be my 1/2 m, the speed of the center of mass squared, plus 1/2 the moment of inertia times I. And this is the moment of inertia about an axis passing through the center of mass. So any object naturally rolling will roll about an axis through its center of mass. So this is my translational piece. And this is my rotational piece. And let me just tell you how you always do these problems is the following. The speed of the center of mass is going to be equal to r omega, which means in this 1/2 I omega squared term, I can replace omega with the speed of the center of mass divided by r. So for example, let me just pull up a different thing. If I have a solid ball, which is rolling, let's say, at speed v, and I want to know what is the total kinetic energy. And you have to have the mass and things like that. I just want to tell you how all these problems go. Is you end up replacing the 1/2 I omega squared term. Well, let me just do it. So if I have a solid ball, my kinetic energy of rolling is going to be 1/2 m times the speed of the center of mass squared. And that's my translational part just because it's moving through space. And I have a 1/2 the moment of inertia about the center of mass times omega squared. How you always end up doing these problems is you replace I with some sort of function, which will be mr squared times some number, depending upon what kind of object it is. And then omega, you're going to end up replacing with the speed of the center of mass divided by r. So for a solid object, a solid ball, was it this one? I did it on lecture notes? No. So these moments of inertia we're giving you, you want to put these on a cheat sheet or you'll have open notes. But depending upon what the object is, I'm going to replace I, the moment of inertia, with some function. So if we're talking about a solid ball, my moment of inertia is 2/5 mr squared. So this problem we're looking at is a solid ball. So what I would do for my kinetic energy term when we're using conservation of energy is I'm going to replace I with whatever objects I'm looking at its moment of inertia. So for a solid sphere, it is 2/3 mr squared. And then I'm replacing omega with v divided by r. And what I get then is 1/2 m speed of the center of mass squared plus 1/3 m times the speed of the center of mass squared. These are the same m's. Which in this case, what is a half? This is 5/6 mv squared. So anytime you're doing a problem where an object is rolling, you're going to have an additional kinetic energy term. And the way you handle that rotational kinetic energy piece, this 1/2 I omega squared, is you replace the moment of inertia with whatever equation is appropriate for the object. If it's a solid ball, 2/3 mr squared, so on and so forth. And then you replace omega, which is the angular speed, with v over r. Okay, let's just do one problem, and then I think we'll be good for today. So let's look at an example problem. Let's do just problem 12a. A solid steel ball of mass 0.5 kilograms and diameter 20 centimeters. Keep in mind, this means that the radius is 10 centimeters, is held in place against a spring with spring constant 100 newtons per meter, compressing at a distance of 30 centimeters. The ball is then released from rest and rolls without slipping along a horizontal floor. It then makes a smooth transition to an inclined plane, rolls without friction up the plane as shown in the figure below. Question is, how far up the inclined plane does the ball roll before coming to rest? How fast is the ball rolling when it's rolled 1.2 meters up the inclined plane? So keep in mind, just to remind you, what is our really big giant energy equation? It was the work done by all external forces plus technical difficulties, plus my initial kinetic energy, plus my initial gravitational potential energy, plus my initial elastic potential energy equals my final kinetic energy, plus my final gravitational potential, plus my final elastic or spring potential, plus any change in thermal energy. So this should be UG initial and U spring final. Same exact equation as before, but now if the object is rolling, these kinetic energy terms have to include both the translational kinetic energy and the rotational kinetic energy. So now my K is going to be 1/2 m speed of the center of mass squared plus 1/2 I omega squared. And again, ultimately, that's just going to turn into something times mv squared once you replace I with whatever the particular equation is for that object, and once you replace omega with v over r. Okay, so let's look at this problem. How far up the inclined plane does the ball roll before coming to rest? So again, you should still define your system. And remember, if you want to use gravitational potential energy, the Earth has to be part of your system. If you want to use elastic potential energy, the spring has to be part of the system. So let's define our system as the ball, the Earth, and the spring. In that case, there are external forces acting. I do have as an external force the normal force acting on the ball. But the work done by the normal force is going to be equal to 0 because the normal force is always perpendicular to the displacement. So if that's the case, I'm going to let my initial condition for part A be when the spring is compressed by 30 centimeters. And I'm going to let my final condition be when this is at its highest point. And what they want to know is how far up the incline does it move. What we're going to do is figure out how high it gets to, and then from that we can use trigonometry to figure out what D is. Okay, let me maybe do this on a different one. So we've got 0.5 So let's do this here. That was example problem 12A. Problem 12-A. So initially the spring is compressed by 30 centimeters. And then at the end, the spring is no longer compressed, but the ball gets up to some final height, y final. And to be clear, let's just define my y equals 0 to be when the ball is at the ground level. So if I look at my big giant equation for energy, I have the work done by all external forces plus my initial kinetic energy plus my initial gravitational potential energy plus my initial elastic potential energy equals my final kinetic plus my final gravitational potential plus my final elastic potential plus any change in thermal energy. 1, 2, 3, 4, 5, 6, 7, 8 terms. And keep in mind, these kinetic energy terms now have 2 forms of kinetic energy, both translational and rotational. So for this part A, how many of these 8 terms are non-zero? How many of these terms survive? The answer is not 1, 2. Normal force is not doing any work, so there's no work done by external forces. This ball starts at rest. It's not moving. It's not rolling. Oops, that should have been K initial. Started at rest. My gravitational potential energy, since I did find y equals 0 at the ground level, is 0. So initially, all of the energy is just the elastic potential energy stored in the spring, 1/2 K delta x squared. Then when it's at the highest point, it's at rest again. So it's got no kinetic energy. The spring is no longer stretched or compressed, so there's no elastic potential energy stored in the spring. There is no thermal energy being generated. And so the end result is the final energy is just the gravitational potential energy. So what I get is 1/2 K times delta x initial squared equals 1/2 or equals mg y final. Initially, it's all elastic potential energy stored in the compressed spring. At the end, it's all gravitational potential energy of the object or the ball at its highest point. So let me just skip the math. You can just solve for this. We've got everything we need. We've got the mass, we've got K, we've got delta X, which you will get for Y. Glasses, glasses, glasses. What you'll find is that Y final is 0.92 meters. That's the final height the ball gets to. But this particular question was how high or how far up the ramp does it go? Well, we were told that this ramp is 30 degrees. And so just from trigonometry, let me just call that D, what I could get is my distance up the ramp is going to be 0.92 meters divided by the sine of 30 degrees, which ends up giving me 1.84 meters. So that first part, pretty straightforward. Going back to this, why did it give me that? So initially, all the energy is the elastic potential energy stored in the spring. Then at the end, it's all gravitational potential energy of the mass in an elevated position. But now for part B, we want to know how fast is the ball rolling when it has rolled 1.2 meters up the inclined plane. So in this case, we want it when it has moved up the inclined plane by 1.2 meters. And let me just skip a quick little step. What I really want to know if I'm looking at energy is what is the height when it's moved 1.2 meters up the plane. And that height, when it's 1.2 meters for this case, my Y final would be 1.2 meters times the sine of 30 degrees, which is just 0.6 meters. So we know that it would go 0.92 meters high at the very top. But now what I want to know is when it's only at an elevation of 0.6 meters, how fast is it going? So let's go back to this right here. Oops. And again, so this is part B. Cannot seem to get this pen thing down. So this is part B. So again, I still have this giant work done by external forces, plus my initial kinetic energy, plus my initial elastic potential energy, plus my initial gravitational potential energy equals final kinetic plus final elastic potential energy plus final gravitational potential energy plus any change in thermal energy. Same situation, starting when the spring is compressed by 30 centimeters. So again, normal force is not doing any work. The ball starts at rest. I'm defining y equals 0 to be the elevation the ball is at to begin with. So initially, all of the energy is still just elastic potential energy 1/2 k times delta x initial squared. But now it's not at its highest point, so it's still moving. So my final kinetic energy term, well, what's 0 now? There is no change in thermal energy because there's no friction. And the spring is no longer stretched or compressed, so there's no elastic potential energy. So now the energy is the kinetic energy of the rolling sphere and the gravitational potential energy. So what I'm going to have is my final kinetic energy is going to be 1/2 m times the speed of the center of mass squared plus 1/2 I, the center of mass, times omega squared. And then I'm still going to have this mgy final term. So putting it all together, what I get is initially, all of the energy is the elastic potential energy stored in the spring. At the end, while it's still moving, I've got translational kinetic energy because the center of mass of the ball is moving. I've got rotational kinetic energy because it's rotating as it's rolling. And I've got gravitational potential energy. So the only real new thing if something is rolling is I have to consider the rotational kinetic energy. So if a block slides down, it's going to behave differently than a ball rolling down. A sliding block only has translational kinetic energy 1/2 mv squared. A rolling ball has both translational kinetic energy and rotational. Now this piece here, you're always going to treat the same way. And what you're going to do is you're going to replace the moment of inertia with whatever the appropriate equation is, and you're going to replace omega with v over r. So what was this? Was this a solid? So this was a solid ball. Oh, solid ball. I just realized, I think, did I do a previous something where I said 2/3? Anyway, I might have made a mistake previously if I used 2/3 for a solid ball. Okay, so my I for a solid sphere is 2/5 mr squared, and my omega I can write as v over r. So this 1/2 I omega squared terms becomes 1/2 times 2/5 mr squared times v over r squared, which is really what? 1/2 times 2/5, it's 1/5 m v squared. So that's pretty much how you're going to end up handling any rolling object, is you take that 1/2 I omega squared term and you turn it into some number times mv squared. So now what I have is 1/2 k times delta x initial squared equals 1/2 m v squared for my translational kinetic energy plus 1/5 m v squared for my rotational kinetic energy plus mg y final. And again, let me just skip this last step. So everything is known except for the speed of the center of mass. We have all of these values. All we're doing is solving for that. And what you'll find is that once you solve for it and plug in all the numbers, you're going to get the speed of the center of mass being 2.1 meters per second. Booyah. All right, let me see what that is. So a solid sphere should be 2/5 mr squared. A spherical shell should be 2/3 mr squared. And I think I might have mixed that up earlier in the video. Okay, little preview going forward. Chapter 12 is a huge chapter. I'm probably going to skip angular momentum just because there's some things I need to get to towards the end. Oh, we got physics 4b. Anyway, there's certain things I need to get to that you're going to need in physics 4b. So I'm going to end up for the last 2 weeks sort of just picking and choosing the most important topics. For chapter 12, I'm probably only going to cover torque. That'll be the last new thing in chapter 12. So I'm probably going to spend 1 or 2 more days on chapter 12. And then we got maybe 4 days to cover 3 chapters. So I'm going to choose just specific parts of chapters 15, 16, and 17. Probably just a little bit of simple harmonic motion and a little bit of waves, but I'll be specific about exactly what we're covering. And in terms of labs, we're pretty much done labs except for this last lab that you got 2 weeks to do. And I'm seriously considering just not doing any PLCs for the last 2 weeks. Well, let me just say that I've been really happy with the number of people that have been attending the live Zoom sessions, and people have been really great about uploading their homework to Mastering Physics. I sent out grades to everybody. The class is doing extremely well. The class average right now is like an 85.1 or something. Tons of A's and B's and things like that. Yeah. So we just open it up. Questions I can answer about anything I covered today in chapter 12 or anything just about anything.
I wanted to talk to you about a potential lab idea.
Okay. Oh, why is that so? Okay, let me do that. Let me, Robert, let me just see if there's any non-lab ideas first, just in terms of questions from chat.
I have a question.
Okay.
I just try to look at the Celebration 2 solutions and it.
Somebody told me that I'm getting the page error, so I'll fix that soon.
Okay, thank you.
Yeah, I just, I linked it. I guess I just didn't upload the file. So I will do that in the next half hour.
Thank you.
You're welcome. If anybody doesn't, if there's no physics questions just on chapter 12 or the remainder of this semester, gonna take out lecture, bring in office hours. Thank you for everybody who joined me live. I'm gonna hang around for about 15, 20 minutes if anybody has any questions for office hours. Thank you, everybody. Have a wonderful weekend. Say, Robert, do you want to just run that idea by me?
Sure, yeah. I kind of wanted to play with center of mass and look at different things. So
you mean, by play with, you mean do a physics experiment with.
Right, yeah. And the thing I wanted to experiment on was when we change the center of mass, like what's the most efficient center of mass for like coasting, or like as far as like comparing velocities, dropping cylinders, or not dropping them, but rolling cylinders down a ramp and then just looking at which one finishes first, kind of thing.
How are you going to determine the position of the center of mass?
Well, I think the 2 easiest cases would be like a solid and then like a hollow disk, like a solid disk and then a hollow disk.
Right.
And then, I don't know.
No, you're not looking at the center of mass as much as looking at the moment of inertia.
A moment of, yeah, exactly. Which.
Okay. So like the center of mass of any kind of regularly shaped object should just be right in the geometric center.
Right.
So
yeah. So I guess, yeah, mine is more about the moment of inertia. Exactly. Yeah.
So yeah, you could do that. Keep in mind, like if you're going to look at something with an object rolling down a plane, acceleration g sine theta doesn't apply when an object is rolling down an inclined plane. That's just if an object is sliding down an inclined plane. So depending upon what you look at, if you're looking at how long it takes or acceleration or something like that, you're going to have to do a little bit. It's in the book, and I could help you out with it. But the equations are a little bit different once you start taking into account rolling motion.
Right. Yeah. That's. I saw a demonstration last night. I was watching a video, and he was dropping these objects at the same time, and you could clearly see that one was bigger than the other, but because they were both solids, they would finish at the same time. So that was really cool. Well, I was thinking that it would be cool to kind of experiment further with that and check out changing those moments of inertia, basically.
I like that idea. One thing I would then say is just try and get some sort of testable theory.
Okay.
Like, you want to be able to do enough trials so you have like a standard deviation, a standard error, so you can test it out, not just rolling it down and be like, oh, I thought this was going to win and it won.
Okay.
So try to make it a little bit more, error analysis that you can do than just these things are rolling down and I want to see which one hits first.
Okay. Yeah, I will play around with it then, and I'll
Excellent.
talk to you again.
Yeah, no, I like that idea.
Cool. Thank you.
Yep.
Hey Joe, it's Grant. I had an idea for the lab.
Okay.
That I was kind of thinking through, kind of involving, I guess, projectile motion and juggling.
Ooh. Okay. Let's hear it.
So I was either going to go to the store and weigh out some fruit so that I could have the mass, and then didn't really think out through what else I would need to do for it, but just like get a couple of different masses and maybe try to calculate either the force or just time it. I'm not really sure what I would be doing for that.
So yeah, I'm gonna need more information.
I just wanted to know if I should keep thinking on that, or just kind of like go more off of one of the ones that you.
So the thing about projectile motion is, in order to do any kind of calculations, you need to know the speed that you're launching it at. And that's something that you need to think about how to do. So, I had the idea if you had like rolled something down an inclined plane and then it went off a horizontal surface, you could use conservation of energy to figure out how fast it's going at the bottom. So then you could predict using projectile motion, like how far away it might land. But if you're just like launching an apple or throwing an apple, you need to be able to measure the speed and the angle that you're launching it at so that you can make some sort of prediction.
Okay, I could maybe do it off of like a video and just time it and get the time for how long it's in the air, and then mass. But yeah, I'm not sure how I would get.
I mean, it sounds like a good beginning. And keep in mind, if you're talking about projectile motion and we're ignoring air resistance, you don't need the mass, right? Because all objects, if I can ignore air resistance, are going to have the same acceleration.
All right. Well, I'll keep thinking about it. Maybe I'll
Okay, sounds good. I'm expecting people to have to come up with a couple ideas, try things, and maybe start over. It's challenging when we were trying to come up with certain ideas. Like if you don't have a scale, if you don't have a force sensor, it's challenging to do these measurements, but that's part of sort of the fun part of it.
All right, sounds good. Thank you.
All right, you're welcome. Maria, Marco, any questions from you two? If there's no questions, I'm going to just pause this video. I'll still hang out for a little bit, but I'm going to pause this and run to the restroom. It'd be a completely